Welcome to our final session this afternoon. Our first speaker will be Tony Aiello, and he'll be talking about QGen, which is one of AdaCore's major products, a model-based engineering tool. Tony.
So I actually get to talk to you about two products today, QGen and SSI, and I'll start with QGen. So QGen is AdaCore's code generator for Simulink and Stateflow. For those of you who don't know QGen, QGen is a great tool. You can develop your models using Simulink and Stateflow, and then QGen will automatically generate Spark or MISRESSAC. Are there folks in the room who use Simulink and Stateflow? I've got one hand. Only one hand? Only one person in the room uses Simulink and Stateflow? All right, well, I'll be talking to you for the next 30 minutes, and hopefully for the rest of you guys, this will still be an interesting talk. So QGen is actually a family of tools. So the centerpiece of QGen is a trusted code generator. So this generator supports about 120 Simulink blocks, and it supports a fairly extensive subset of Stateflow. As I said, with QGen, from these blocks, you can generate either MISRESSAC or Spark. And QGen can also process your models incrementally. This becomes important as you have large models. So if you only change one small part of your model, QGen will only process that part of your model. One of the really nice things about QGen is you're not tied to a specific version of Simulink when you use QGen. So you have the flexibility to change your version of Simulink without changing your version of QGen. This is very important, especially if you have a qualified version of QGen. You also have the opportunity to update your version of QGen without changing your version of Simulink. This is usually not the case if you're using tools from the MathWorks. So if you were using Embedded Coder, for example, you would be forced to upgrade your code generator at the same time that you upgraded Simulink and Stateflow. QGen also generates very consistent code across Simulink versions and across minor layout changes. This can be very important for traceability, which is a key concern for qualification. So that's the trusted code generator for QGen. QGen also provides a unique model debugging capability. So using QGen, you can actually debug code that's been generated from your models on your target. And the really great thing about what QGen does is it gives you the information that comes out of the debugger in a context that's relevant for your models. So if you're used to doing model-based design, then you're used to thinking about your models in the environment of Simulink. You're used to thinking about simulation and looking at simulation results on your model. Now, while you actually execute the code on your target, you can get that same kind of information through the model. So we think that's a really powerful capability. The final piece of QGen is QGen Verifier. So this is a model-level static analyzer. So what we do is we generate Spark from your Simulink and Stateflow models, and then we pass that to CodePeer. And when CodePeer finds problems, because the code was automatically generated, those problems come from the model. So we actually link those problem reports back to the model, thus providing you with a model-relevant error report from the error that was actually found on your executable code. So we feel like this is a really important point because you don't have to wonder what the semantics are behind the analysis that's being performed. You know that the analysis is taking place on the actual code that would run on your target. But you still get very relevant information that you can diagnose and address through your model. So that's QGen Verifier. So those three pieces are what you get with QGen. But what we think is one of the most important parts about QGen is that it was designed from the outset to be qualifiable. And in fact, right now, we're working on qualifying QGen so that you can use QGen for programs that need certification under DO-178C. So that's what I'd like to talk about for most of the rest of this talk. So we know that certifying software to DO-178 Level A is expensive. And in particular, there's many required activities that take place at the source code level. So for example, when you look at your source code, you need to show through testing that you've covered your low-level requirements. You also need to provide specific coverage levels depending on the criticality of the code that you're developing. For example, at level A, you need to show MCDC coverage of your source code through your requirements-based testing. This, combined with the kinds of peer reviews and other analyses that you have to do with your source code, is a significant cost driver for certification. Now, model-based design and automatic code generation is intended to reduce this cost. But that only works if your code generator is qualified. So the promise that we have with QGen is that you won't have to look at the majority of your source code. So what might this look like in terms of workflow? So using QGen, you would start out on a day-to-day basis, developing your models, doing simulation runs, and then doing a quick incremental export with QGen, then doing a quick code generation on that incremental export, and running QGen debugger as needed. So this gives your engineers the ability on a day-to-day basis to work with the tools and to work out problems in the model. Now, perhaps several times a week, you would want to check to make sure that the development activities that have taken place so far stay within the qualifiable subset of Simulink that we support with QGen. So we would suggest that you run a full export through QGen and check to make sure that you're not having any errors on the qualified code generation. Finally, when your behavior is okay, you would take your Simulink model and you would use tools that the MathWorks provides to get coverage analysis of your Simulink model. So this is the point at which you show that you have developed adequate test cases for your model, which serves as your low-level requirements, to show that you fully understand what the model is doing. You would then generate generate code using QGen and re-execute all of those test cases on your target. So this does two important things. So first of all, while QGen is a qualified code generator, and we promise that the source code matches the model, it's very likely that you're not then going to use a qualified compiler to generate your executable object code. So this step of rerunning your model-level test cases on your executable object code enables you to detect if the compiler has injected any errors. Second, in developing QGen, we don't have a particular target in mind. So we can tell you that we match the semantics of the model, but we can't tell you that the source code conforms to any target compatibility requirements that you might have. So by rerunning your model-level test cases on your target, you're able to check for source target compatibility. So with that in mind, what do you get from QGen? You get to take credit for a large number of certification objectives. For example, you don't have to review your generated source code. Because you use QGen, and because QGen is TQL1, we guarantee that you have compliance with your requirements, and we guarantee that you have compliance with coding standards. You don't have to do LLR-based testing of the generated source code because we have already shown through TQL1 that the source code we generate conforms to the semantics of the Simulink model. And you don't have to do specific coverage analysis of the source code because in qualifying QGen, we show that when you have adequate coverage of your model, that coverage will also provide adequate coverage of your source code. So to dig into this a little bit more, I'll look at 4 tables from the model-based standard for certification, and I'll just touch on some of the things that we provide. So here we show you that low-level requirements conform to standards. So this is looking at your model and ensuring that in developing your model, you have adhered to a set of standards that have been selected. And because QGen asks that you stay within a qualified subset, we can give you credit for this objective. Most of the objectives for which you can take credit come from table A5. So these are the objectives that have to do with the source code itself. So things like compliance to the low-level requirements, compliance to your software architecture, you get these essentially for free in using QGen because of the TQL1 story. In table A6, we look at the outputs of integration. This is where we show that executable object code matches our requirements. And by re-executing those test cases in conjunction with the TQL1 story, you can take credit for these objectives. And finally, as I said, when it comes to coverage of your source code, you can take credit for any coverage you've obtained at the model level because of the TQL1 story for QGen. So that's QGen. That's what it gives you in terms of qualification. What I'd like to do now is share with you where we are on our roadmap towards actually achieving this qualification. So our goal, our intent, is to have TQL1 qualification by Q4 2020. So QGen has been selected by one of the largest aerospace and defense contractors in the US. And working with this contractor, we expect to have several DO-178C projects, both at the FAA and at EASA. And what this means for you is that over the coming years, we will continue to work on QGen towards TQL1 qualification, both at the FAA and at EASA. So we have already sent materials to the FAA and to our launch customer for the first stage of involvement, SOI1. This is the stage of involvement at which we disclose our plans for qualification of QGen, and we ask for feedback from the auditors on those plans, essentially to get an okay that what we have selected to do will be viewed as sufficient for qualification of the tool. We anticipate the audit early next year, and we anticipate that qualification will be complete by November 2020 of next year for the FAA. The follow-on qualification for EASA is expected in 2021. And just to give you a little bit more detail, these are the materials that we have already prepared and sent to both the FAA and to our launch customer. As I mentioned, most of these materials focus on planning. So that's where we are in terms of roadmap, where we're going, and where we are in terms of our status. Now what I'd like to do is dive into the qualification approach that we're taking with QGen, because we're actually doing something different here. So instead of following DO-330 for the qualification of QGen, we're showing that QGen possesses the overarching properties. And I'll spend the next several slides telling you what that means. So you might ask, why are we looking for a new qualification approach for QGen? And our answer is DO-330, the tool qualification supplement for DO-178C, is actually based on airborne software certification, and we therefore feel that it's a little bit awkward to use for tools. So DO-330 asks for applicants to come up with substantially similar objectives to those that are required by DO-178C. But tools aren't airborne software, and they differ from airborne software in three critical ways. So first, the hazards for tools aren't the same as the hazards for airborne software. It's generally not a hazard if a tool halts on bad input or because of some erroneous internal state. But for airborne software, if it halts on bad input or erroneous internal state, this is probably an issue because likely that software is safety critical and serves an essential function for the aircraft. So the hazard space for tools is different from the hazard space for airborne software, and thus asking for the same objectives probably doesn't make sense. Second, tools are fundamentally COTS. They address multiple heterogeneous usages. We see this with QGen because QGen has both a qualified use case and also a non-qualified use case. And this is important to us. It wouldn't make good business sense if QGen was only a qualified tool. We also need to be able to use QGen in non-qualified settings. Current standards don't provide really great ways to deal with these kinds of heterogeneous use cases. Also, QGen as a tool was developed using COTS components, and the use of COTS components for a system that needs to be qualified under these kinds of standards is typically challenging. Finally, tools must evolve, and requalification must support this evolution. So you would not be happy if we developed a tool like QGen, certified it today, and then didn't change it over the coming years. You would want us to be able to do things like support new blocks in Simulink or new features of stateflow so that your developers could use the tool more efficiently. You would want us to be able to support new versions of Simulink and stateflow as they come out. You would want us to address issues that might be found in the tool over the course of its use so that you didn't have to work around those kinds of issues. And that evolution is difficult to achieve under current standards. So this is our motivation for seeking a new qualification approach. At the same time, the FAA has been asked by Congress to find ways to streamline certification. And this has occurred for a couple of reasons. So one reason is that the burden of current certification processes can actually be seen to be having a negative impact on overall airspace safety. So here's a simple example of what I mean by that. So if we consider small GA aircraft, there's a failure mode that occurs relatively frequently where a pilot will lose situational awareness, not realize that the aircraft is beginning to roll, until either there's a significant problem or possibly the aircraft departs from controlled flight. So we could solve this relatively easily by putting a simple wings leveling autopilot on these small GA aircraft. But a wings leveling autopilot is a safety critical function, and it would therefore need to be certified to a high level of safety. Not the same as for transport aircraft, but still, the certification burden is significant. And when we do that, and when we pay the cost for that certification, we find that we price that kind of function out of the range that makes it appealing for pilots of small aircraft. And so what we've actually done is, in seeking to have safe software, which is good, we've actually potentially reduced the overall airspace safety by taking away a function that could be saving lives. So second, the FAA is faced with new and different systems that are trying to gain access to the airspace, especially UAS. And just like with tools, UAS often have different kinds of hazards from other aircraft. They often use different underlying technologies, including a lot of use of COTS, and they often seek to evolve very rapidly. And current certification standards don't support the integration of UAS very well. So the FAA is seeking a novel approach that will allow it greater flexibility in certification. And what they want to do is to tailor the evidence that's sought so that it better fits the particular needs of the system and its application. And the goal of doing this is, of course, to reduce cost, but they don't want to reduce safety. And so I'd like to say this is all not about shortcuts. We're not trying to find shortcuts. The FAA is not trying to find shortcuts. We're trying to find more meaningful evidence given the system and its application. So with that in mind, the FAA convened a working group, and this working group surveyed a broad set of standards and asked itself, are there commonalities amongst these standards that we could see as meta objectives? Are all of these standards essentially trying to solve the same problem by looking for the same kinds of things in the systems that are seeking certification approval? And in finding these, the FAA named them the Overarching Properties. And so this working group is called the Overarching Properties Working Group. They identified 3 properties, which they named intent, correctness, and innocuity. A lot of time and effort went into the creation of these definitions. These are very precise. I think these are good definitions, so I'm actually going to read them to you. Intent is the defined intended behavior is correct and complete with respect to the desired behavior. Correctness, the implementation is correct with respect to its defined intended behavior under foreseeable operating conditions. Innocuity, any part of the implementation that's not required by the defined intended behavior has no unacceptable impact. Now I'll pause at this point and make 3 observations. So first, these terms are a bit precious, and that was actually done intentionally. So the Overarching Properties Working Group was concerned that if they used common terms, the typical overloading of these common terms might drive people to not consider the detailed definitions and therefore misunderstand the properties. So they chose precious terms for these to drive people towards the definitions. But that being said, if we look at intent, it seems fairly clear that intent is talking about requirements and can therefore be thought of as validation. And correctness is talking about implementation, so it can be thought of as verification. And innocuity is kind of an odd duck. So innocuity is really focusing on extraneous behavior. It's really asking you if you've incorporated COTS, or if you're building a component that's meant to be COTS, it's likely the case that there is some piece of the functionality that's not actually required by your system. And this extraneous functionality could undercut your safety assessment, and so you need to look at it. And that's what innocuity asks you to do. It asks you to look at any kind of extraneous functionality that you might have and ensure that it doesn't violate your safety. Second, if we look at these overarching properties, safety doesn't appear anywhere. And that might seem odd. But the Overarching Properties Working Group was thinking about these properties in the context of an item, a component, that would be integrated into an aircraft system under development. And so they expected that at the aircraft level, a system safety assessment would already have taken place. And so in the overarching properties, this pre-existing safety assessment is taken as a prerequisite for the application of the properties. And so intent asks, did you satisfy any safety requirements that might be needed by this safety assessment? Correctness asks, did you satisfy these safety requirements? And inequity asks, does any extraneous functionality undercut this safety assessment? The final point, some of these terms are highlighted in italics, and that's because the Overarching Properties Working Group worked out definitions for all of the terms that they introduce. You'll have these slides available later, and so if you'd like to look at these definitions, you can. My point is simply that a great deal of effort was taken to push the definitions all the way down to ground terms or to reference documents. So these properties are designed to be a different means of compliance to airworthiness regulations. They were designed to be flexible in scope. So the Overarching Properties Working Group imagines that these can be used for software, for hardware, for subsystems that combine multiple items together, possibly all the way up to the aircraft level itself. The intent is that for whatever the application, through a coherent set of artifacts, the overarching properties can be used to seek certification approval. If you're interested in the overarching properties, if you'd like more information, NASA and the FAA put together a document called Understanding the Overarching Properties. The link is here. You'll have it in the slides. This document was written by Michael Holloway. I think he did a great job of putting this together. It's 30 pages long, which seems daunting, but he wrote it in a very narrative style in which he tries to unpack the rationale and explain the properties and how they might be used in a very easy to read way. So I highly recommend this document. So that's the FAA's approach, the overarching properties. Around the same time, a working group was convened in Europe to look at how these properties might be assessed. This group is called RESSAC. And initially what they did is they said, well, we have these properties. We should develop a set of criteria that can be used for assessing whether a system possesses these properties. So they developed a set of criteria and they started playing with them. And what they discovered was they'd effectively recreated the inflexible standards-based approach that they were trying to get away from by posing these criteria as objectives that needed to be satisfied. And so instead, what RESSAC suggested is that we demonstrate possession of the overarching properties by constructing an assurance case. So the certification approach is to demonstrate possession of these properties using an assurance case. And RESSAC defined an assurance case like this. An assurance case is an argument with its supporting artifacts. In the context of the overarching properties, the assurance case is intended to show how the properties are possessed by an item or a combination of items. The argument introduces, summarizes, and provides context for the context and justification for evidence of possession of the properties. Evidence is a reference to a means of assessing the truth of a given premise and the artifacts created or examined in that assessment. Now, I like this definition a lot, which is why I read it to you. One of the reasons I like this definition is that it makes an argument a central part of an assurance case. I also really like this definition because it makes it clear that evidence is a fundamental component of an argument. You can't have an argument without evidence, and that's very clear in this definition. So the assurance case allows us to propose the evidence that we wish to gather, to provide the rationale for the sufficiency of this evidence, and to present the evidence itself. So in essence, by constructing an assurance case for demonstration of possession of the overarching properties, we can construct our certification approach and follow it at the same time while using the argument to lay out the justification for why this approach is sufficient. Now, this term argument, an argument is a conclusion, which is some kind of testable assertion, and this conclusion is supported through reasoning by premises. These premises form the grounds of our arguments. They may be conclusions from other argument steps. They may be artifacts that we're citing as evidence. They may be unjustified, in which case these are assumptions on which our argument is predicated. Now, I think the assurance case community and the safety case community has done itself a disservice by presenting argument in a way that makes it seem entirely novel. But engineers make arguments all the time. We make arguments to ourselves. We make arguments to each other. I'm making an argument to you right now through this presentation. When we're talking about an assurance case, we seek arguments that are explicit, structured, and rigorous. But I'll never say that an argument is formal, because the reasoning that we're using in the argument is logical induction. It's not logical deduction. Where we can use deduction, we should use proofs, and those proofs can be evidence, which we'll bring as premises for our argument. So what do I mean when I say I want the argument to be explicit? An implicit argument is an argument that exists in somebody's head. And the problem with this is that it's not subject to review. There may be missing premises, there may be missing reasonings, and we can't know this because it hasn't been written down and it's very difficult to interrogate it. An explicit argument is an argument that we've written down, and this is beneficial because we capture tacit knowledge, we facilitate communication, and we enable knowledge transfer. An argument serves as really great documentation for your system. If you have new people coming on, they can get a great introduction to not only your system, but why you're building your system in the way that you're building it. And the best part about an explicit argument in the context of certification is that it's now subject to review. So we can set this in front of auditors, and the auditors can look at it and begin to ask us questions. I said we seek arguments that are structured. An unstructured argument looks like this run of text at the left. And the problem is it's very difficult to read this and understand the role that the various parts of the argument or the various parts of the text are playing. By contrast, if we structure the argument, for example, as we've done it at right here, we can very quickly understand the role that each piece of information is playing, and we can begin to ask questions about the argument and possibly shoot holes in it. In my experience, I have set structured arguments in front of people that have never seen them before, briefly explained how they worked, and very quickly people have started to shoot holes in my argument. I consider that to be a win, because if I had put a document in front of them, I think it would have taken much longer for them to get to the point where they can start to challenge it. So, how are we building our structured argument? We're using a modified version of the Toulmin method, which was recommended by RESSAC. So here we have conclusions, which is what we're trying to derive from the current argument step. We have reasoning, which describes how the conclusion can be derived by its given premises. We have backing, which supports the reasoning. It tells us why the reasoning is applicable in this context. And we have the premises, which are the grounds of the argument. We can also introduce defeaters, and what defeaters do is they give us a means to capture specific challenges that have been made to either the soundness of the argument or the truth of the conclusion. So you can imagine that during an audit, if an auditor says, I'm not sure I believe this part of the argument because, we can write that down as a defeater, and then we can introduce a counter argument to explain why that defeater is actually not a problem for the argument at that point. So we've recorded both the challenge to the argument and the solution to the challenge, and that's now available for subsequent audits. Typically, Toulmin's depicted as shown at right, but I think that putting text inside of circles is a really terrible idea. So what we've done is rotated this through 90 degrees so that we list the conclusion at the top, the reasoning, the backing, and the defeater underneath, and then the premises at the bottom. We can then hyperlink from the premises that are supported by conclusions to that conclusion, and it's now very easy to run through the argument and actually follow chains of reasoning down to their leaves. We can also format the argument like a tree. And I really like this tree-like notation because in this way, you can look at sibling relationships in the argument, you can look at cousin relationships in the argument, and begin to understand better how the overall pieces of the argument work together. So how are we using this in QGen? This is a very high-level view of how we're applying this notion of structured argumentation to QGen. So at the top of this, we want to say that we're making a compelling demonstration that QGen is fit for use in the development of safety-critical code. And we do this in two ways. On the left, we look at fitness for use, and on the right, we look at confidence. So in terms of fitness for use, we focus on possession of the overarching properties, and we show that QGen possesses the properties of intent, correctness, and innocuity. We also introduce a specific risk assessment. And this is done because, as I said earlier, the overarching properties assume a safety assessment as a prerequisite for application. But QGen is not being developed in the context of a specific aircraft system, and so there isn't an aircraft-level safety assessment that's already been performed. Instead, what we're doing is asking, what are the critical hazards for use of QGen that might have a safety impact on our end users? And the golden hazard that we've identified is that QGen could generate code that's incorrect, that doesn't match the semantics of the model, but nevertheless compiles. That's the hazard we're concerned with. And what we've done is made a stage-by-stage hazard analysis of QGen to find ways in which QGen could misbehave that might cause this hazard to happen. We then introduce safety requirements and satisfy those safety requirements, thereby removing the hazard. We're also considering hazards that might arise from the specific way in which QGen was developed by looking at things like dynamic memory allocation, dynamic dispatch, and ensuring that those uses of Ada language features aren't going to pose a problem in QGen. So that's the fitness argument. On the right-hand side, we have a confidence argument. And here what we're doing is we're arguing that the evidence that we're producing is of high quality. And we're doing this in very traditional means. So we're following the kinds of processes that you would expect from a qualification activity, looking at the way in which we've developed the tool, looking at the way in which we're doing quality assurance, looking at configuration management and certification liaison, and arguing that all of those activities support confidence in the demonstration of fitness for use. So that's QGen. That's how we're qualifying QGen. We're showing that QGen possesses the overarching properties, and we're doing this through the development of an assurance case. And this is supposed to be finished by the end of next year. Just a quick summary, you can take credit for a lot of objectives using QGen. So I won't read this list to you, but you'll have it available on the slides and in the documentation on QGen. One final point that I'd like to make. So we're following a novel approach to qualify QGen, but I don't want that to seem to you like a risk. I want you absolutely to feel like you can use QGen on your programs and not be afraid that you won't get qualification credit. AdaCore and our partner Vericel, who's helping us with the qualification, guarantee that we'll give you timely deliverables to support all of your stages of involvement with the FAA, that we're going to address any identified defects, and that all the materials we provide will ultimately be acceptable to the DERs and the ACOs. So although we're doing something different, this is not a problem for you. So that's QGen. If you have any questions, I'd be delighted to answer them. Please come and find me during the cocktail hour, or find Clément, who's in the back. He has a QGen sticker on his badge. We'd be happy to answer your questions. Now, I'd like to talk to you very briefly about SSI. So SSI is a new product direction that we're following at AdaCore. So when we consider current development practice, we note that teams tend to work very independently in each development phase. So often it's the case that one team will develop requirements using some tool, and then another team will develop architecture using some tool, and then yet another team will develop code using a tool. And although these teams communicate through artifacts, our concern is that these independent silos in which these activities take place might lead critical properties to be lost. So what we'd like to do with SSI is we would like to build bridges that link together each one of these stages. So we would like to show that system-level properties, once they're identified, are maintained throughout the development process. That's our goal. So we're developing tooling to support this. And in developing these tools, what we want to do is we want to use existing tools and existing processes like SysML, like Simulink, rather than ask our customers to use new tools and to change current development practices. So I'll dig into this a little bit more. So if we look at the V model, on the left-hand side we have design. On the right-hand side we have verification and validation. And this model of development is problematic because errors are typically introduced during design, but they're often not introduced until system integration or other verification activities. So what we would like to do is we would like to identify errors earlier. So one way we can do this is using formal methods. We've talked a lot today about tools like Spark and like CodePeer, which give us the ability to find defects earlier. Spark in particular is very powerful and can give us a lot of capability for ensuring that system-level properties are maintained. So using Spark, we can show that an implementation satisfies its contracts. And if those contracts include critical security properties, or critical safety properties, or even critical functional properties, we can now have a great deal of confidence that the software, as developed, actually exhibits those properties. The challenge that we've seen at AdaCore is that it can often be difficult for engineers who are developing the code to have in mind the kind of system-level properties that might be needed to show safety, security, or functionality. And the reason this occurs is because these properties naturally flow down from system requirements. But there's a gap between the system requirements and the level at which the code is developed. So what we want to do with SSI is we want to provide a means to capture these requirements, these critical properties, higher in the development cycle, and then carry them down through the stages of development until we reach the point at which they can be expressed in a language like Spark. So SSI allows us to make better use of formal methods. So that's the first thing. The second thing is that we'd like to prevent the introduction of errors during the design phase entirely. So one way we might do this is with automatic translation. So using a tool like QGen, we can ensure that after a model has been developed in Simulink or Stateflow, after it's been simulated and the engineers are happy with it, when the code is generated, no further defects will be introduced. This is the basis of the qualification story. And this works really well at a low level, but if we look higher up the V to this level of system requirements or to high-level design, what we see is there's a gap. The languages that are used for capturing requirements or capturing high-level design don't currently have good automatic translators that can take us from those representations down to a representation like Simulink and Stateflow, where we can complete the translation. So what we'd like to do with SSI is we would like to support more automatic translation at a higher level. So here, our vision is to take a language like SysML and to translate it into a skeleton in Simulink, where we would lay out the subsystems and the connections between the subsystems so that the basis of the detailed design matches what was done at the SysML level. Then, engineers would come in and they would complete the subsystem by filling them out with blocks. So together, this notion of better support of formal methods and better support of automatic translation, we feel gives us a story in which we're better supporting property continuity. We'd really like to see properties that are identified at the system level carried through detailed design into code so that we have a complete story of traceability and translation and proof from the highest level of system design all the way down to the code. So that's the goal of SSI. Right now, we're at the very early stages in working on this. So we've developed some prototype tooling. Our tooling integrates with Cameo System Modeler, which is a tool for SysML and UML modeling. We've developed a plugin that exports information out of Cameo, and this then goes into a plugin for QGen that brings that information into MATLAB and Simulink. So to get a little bit more detailed about this, we currently support the kind of information that you would typically specify in SysML using block definition diagrams, internal block diagrams, and requirements diagrams. We can take information about system structure, which shows the way in which components are composed. We can take information about interfaces, which tells you the kinds of information that flow into and out of a component. And we can take information about value types, which tell you the data types that are going to be exchanged by components, and use that to generate Simulink subsystems with ports that are correctly typed. We can take information out of the internal block diagram, which gives us the information flows that connect these components together, and use that to generate connections so that the subsystems in Simulink are connected together. Finally, and most importantly, we can take information out of the requirements diagram, where requirement satisfaction is linked to components, and where formal constraints have been introduced, and we can synthesize synchronous observers that can execute at the Simulink level. A synchronous observer is a small subsystem that executes concurrently with the Simulink model and continually evaluates signals to check if they satisfy some contract. If not, the simulation is stopped and an error is raised. So we can automatically generate synchronous observers from the information contained in these requirements diagrams when the constraints are formalized. So that's where we are with our prototype today. Here's a quick summary of where we would like to take this, and I hope in the next couple of years I can come back and show you what we've done. So we'd like to improve our handling of SysML. We'd like to support more elements of SysML and more robust workflows, more interactions amongst these pieces of the model so that we can build a richer starting point in Simulink that can then be completed. Model translation is great. Model layout is very challenging. And in order to do model translation, you essentially have to build a starting layout that engineers won't find completely unacceptable. So we need to improve automatic layout. This is a challenge for Simulink. We'd also like to have better traceability between SysML and Simulink. So right now we can generate the skeleton. We'd like to get to a point where we can jump back and forth between the Simulink model and the SysML model so engineers can always see where the requirements for a component in Simulink came from or what a component in SysML will look like in the eventual Simulink diagram. And finally, we'd like to explore opportunities for analysis. So we'd like to conduct analysis within SysML so we can look at these formalized requirements and ask if they're consistent, ask if they're complete, ask if they have entailment of other higher level properties. And we'd like to be able to prove that synchronous observers that are generated in Simulink are always satisfied, for example, using QGen verifier. So this is our goal for SSI. If you are interested in this, again, please come and talk to me. I'd be delighted to tell you more. And I'm particularly interested if any of you have SysML models that you might be able to share with us. One of the things that we are seeking as we work on this tool is information about how you and industry use SysML so that we can make more informed decisions about the kinds of model elements that we support and the kinds of workflows that we support. Thank you.